today is about the triaxial test. All right. So about the triaxial test we are going to discuss, and what is the basic advantage of this test. All right, and how we can replicate the various stress condition, basically the total stress and the pore water pressure. All right, so the total stress and the pore water pressure. So these are the two most important parameters that we need to control, so that we can obtain what will be the response of the soil to the various loading conditions when we load the soil, and there will be changes in the pore water pressure. So to replicate that of what is happening in the field in the laboratory, we are going to do the triaxial test. Now before going to the triaxial test, in the previous classes we have already discussed what is effective stress. So at a particular depth, if we have an element, so the total stress at that point will be the weight of the entire soil mass, water, or whatever it is on top of this element. All right, everything on top of this element divided by the unit areas, acting per unit area. So we will have the total stress. So that is the sigma. All right, and if we want to find out the pore water pressure here, so that is the height of the groundwater table multiplied by the unit weight of water. So we will have the pore water pressure. So if we subtract that pore water pressure from the total stress that is acting there, we will have the effective stress which is acting at that point, as we have discussed in our previous classes. So here what we can measure is or obtain is the total stress and the pore water pressure. So these two elements, these two parameters we can measure and obtain, and from there, when we subtract the total stress, the pore water pressure from the total stress, we get the effective stress at that particular point. So we may have different total stresses in different directions. So here there is an element, we have sigma 1 in the vertical direction, sigma 2 in the horizontal direction in x-axis, and then sigma 3 in the other horizontal direction in the y-axis, that is in the y-axis. So stresses in a soil mass may be different in different directions. All right, but the pore water pressure at a particular point is always of the same magnitude in all directions. So to obtain the effective stress at a particular point, so in the z direction, we have sigma 1 dash equal to sigma 1 minus the pore water pressure at that point. Similarly, in the x direction, we have sigma 2 dash equal to sigma 2 minus the pore water pressure in that direction. So the effective stress similarly in the y direction will be sigma 3 dash equal to sigma 3, which is the total stress in the y direction minus the pore water pressure. So pore water pressure is same in all direction. So as we have already discussed. So now let us consider a case. Now this is a soil strata. All right. So this is a soil strata. We already have a groundwater table in the soil. So this is the soil strata. Sorry. So this is a soil strata. We already have a groundwater table. So if we insert standpipe into the ground, we will see that the water table or water level rises up to the same height in all of the standpipes. All right. So this is a steady state as we have discussed here and here. So here at any point, if we want to measure the pore water effective stress, so it will be sigma dash is equal to sigma minus u. Now suppose we suddenly load this soil element at a point here. All right. So as soon as we load it, the first thing that will happen is the pore water pressure will shoot up. All right. The pore water pressure will increase. Now why it increases, we will see in the later slides. All right, so we need to analyze how it rises, why it rises, and what is the magnitude of the rise. So as soon as we load the soil, first of all, there is a rise in the pore water pressure, and that pore water pressure will with time slowly dissipate out, and ultimately the final stage will be the same as the initial stage, but here what we will have is the additional load still acting on the soil. So what will happen in this case is, as soon as the pore water pressure increase, now as soon as we load the soil, the pore water pressure increases. So here we will have now an increase in delta sigma, all right, and an increase in pore water pressure. Now, if the increase in the pore water pressure is equal to delta sigma, all right, if the pore water pressure is increase in pore water pressure is equal to delta sigma, then the effective stress will not change. So delta sigma dash will be constant. It will be zero. All right. So delta sigma will effective stress, that is sigma dash, will be same as the initial state. But the pore water pressure is increased. Now with time, as the pore water pressure will gradually reduce, there will be settlement in the soil. All right. So that settlement in the soil, we call it the consolidation settlement. And that particular amount of settlement, how much it will settle, all right, what will be the time required to settle, all right, all those things will be covered in the consolidation chapter, all right, all the settlement due to the consolidation chapter. In that particular chapter it will be covered. The thing is that initially we have a soil, all right, and that soil is under a steady state, so we have a total stress acting on the soil, and in that case we also have one pore water pressure, groundwater table, all right, so we have a total stress and the pore water pressure, so we have a constant effective stress state, that is sigma dash, which is equal to sigma minus u. Then suddenly what happened is, now the total stress is now increased by delta sigma. So what happened is the pore water pressure also got increased. Now if delta sigma is equal to delta U, then we will have the effective stress state unchanged. All right. So that means delta sigma dash will be 0. But with time, what will happen is that this delta U, the delta U increase in pore water pressure, whatever it was increased, so slowly ultimately it will revert back to the original state. So now in this case we have delta U is equal to 0. So now what we will have is that the effective stress is now increased, so we will have a delta sigma dash which is equal to the delta sigma which is applied in the soil. So the total effective stress now is delta sigma dash plus delta sigma dash equal to sigma plus delta sigma minus U. All right, so U was the hydrostatic pore water pressure, which was the initial case, so that is the groundwater table, so it will always remain in that case. All right, in that position itself, so we will have the same pore water pressure. Only thing is that the excess pore water pressure which was developed, with time it will dissipate out. All right, and there will be an increase in the effective stress. Now, so we see that at time suppose t equal to 0, we suddenly loaded the soil, so we increase the soil up to delta sigma 1 suppose, and that load is now remaining on top of the soil. Now as soon as it was loaded, there was a rise in the pore water pressure. So this is the hydrostatic pore water pressure. So this is the hydrostatic pore water pressure. Right, so this amount, which is equal to U, right, or UI we can say here, and this additional region of increase of pore water pressure, we call it excess pore water pressure. So with time, what will happen is that this excess pore water pressure will dissipate, but the loading which was applied on the soil surface, it is still there. So that load has to be transferred to somewhere, right? So what will happen is that with time, the pore water pressure will dissipate. with time the pore water pressure will dissipate. All right, or the excess pore water pressure. All right, so delta U basically, and it will come to the point of U or UI, the initial pore water pressure. All right, which is the hydrostatic condition here. Now, when the pore water pressure will dissipate, the effective stress within the soil will increase. And while there is an increase in the effective stress, the soil will undergo consolidation settlement. Of course, that part will be, we will discuss that in a different chapter altogether. Thing is that there is a correlation between the excess pore water pressure and the change in the effective stress in the soil. So here we consider again another soil strata. So we have a groundwater table here. All right. So we have the soil, so which has a unit weight. So suddenly again we load the soil on top. So we have a load. So what will happen is that as soon as we load, so we have the pore water pressure, this one. So starting from 0 here, we have the pore water pressure. So this is the pore water pressure. As soon as the soil is loaded, the pore water pressure will increase. So the pore water pressure will increase, and then with time it will slowly and gradually dissipate, and ultimately it will revert back to the original state or the hydrostatic state. So in terms of total stress, if we plot, so we will see that this is the increase in the total head, sorry, in the terms of total head. If we plot the pore water pressure, this pore water total head, if we plot, so we will have a increase in head, and then with time the head will decrease, as we saw in the case of the standpipe. So the pore water head got, it shoot up, all right, and then with time it slowly got decreased. But what about the load which was applied? So that load is still there. So the load is still there. So the pore water pressure got increased, all right, and then with time it will slowly dissipate out. All right, so this hydrostatic pore water pressure or the static pore water pressure will always remain there, all right, and the excess pore water pressure which was developed, that will gradually dissipate with time. Now, as it will gradually dissipate, as we have discussed earlier, so it will dissipate with time, and with the dissipation of the pore water pressure, the effective stress within the soil will increase. Now, we need to replicate these conditions in the laboratory. All right, we need to replicate. All right, so when we apply a load, there will be an increase in pore water pressure, and then gradually the pore water pressure will dissipate, and there will be an increase in the effective stress in the soil, and there will be consolidation within the soil. So we need to replicate. What will happen if when we load, suppose when we load, of course there will be increase in the shear stresses as well within the soil. All right, it will not be that only the confining stresses are increased. There will be only, or the normal stresses in the soils are increased. There will be an increase in the effective stress. Now, as soon as a load is applied, all right, so we apply a load, so the total normal stresses will increase. So the total normal stresses, which are the sigma 1, sigma 2, and sigma 3, they will increase, no doubt. All right, but with that the shear stresses will also increase. The shear stresses will also increase. Now, as soon as the soil is loaded, what will happen is that the increase in the total stresses, normal stresses, will be taken up by the pore water pressure. So the effective stress will remain zero in this case. There will be no change in effective stress. So the initial effective stress, that is the delta sig, I mean the sigma dash, will remain constant. So in that case, we see that the effective stress which was initially in the soil, that is remaining constant, but there is an increase in the pore water pressure, all right, and there is an increase in the shear stresses. Now, can these shear stresses cause a failure in the soil, all right, or can there be a shear failure within the soil, all right? That is in a very intermediate time or within very short span of time, can there be a failure in the soil? And what will happen when the consolidation has occurred, when the excess pore water pressure has dissipated? What will be the condition then? So to replicate these various conditions, all right, so especially the development of pore water pressure, that is delta U, all right, and with development of pore water pressure, how the effective stress changes, all right. So when we apply a load on the soil, that is delta sigma, all right, so we need to do the triaxial test, all right. So triaxial test, there are some advantages, as we will see. What are the basic advantages we will see? So we need to do the triaxial test. So what is basically the triaxial test? So we have the triaxial cell. First of all, we have the triaxial cell, and it is basically a, we can say it is like a cylindrical element, all right, encasement, all right. So inside it is a hollow. So this is a hollow cylinder, and inside we have a pedestal here. So on this pedestal we can put the soil sample. On this pedestal we can put the soil sample, and with the help of water pressure, with the help of water pressure, we can replicate the total stresses in the soil, all right. We can replicate the total stresses in the soil. So we can replicate the total stresses in the soil. Now in this case, it is basically, the loading is basically axisymmetric. So if we consider the element, all right, if we consider the element, so we have sigma 2 and sigma 3 and sigma 1, all right. So here what we can do is sigma 3 is equal to sigma 2, all right. So that is one limitation. So sigma 3 is equal to sigma 2 in this case, and we can apply sigma 1 through the loading ram. So this is the loading ram. So basic concept is that we can apply sigma 3, we can apply the confining total stresses onto the element, all right, confining total stresses onto the element using the water pressure inside the cell, all right. And this sample, it is encased in rubber membrane. So this water inside the cell, it cannot go into the soil. Only thing is that it will exert the pressure, whatever pressure we have applied onto the water, that pressure it will exert onto the soil sample at all points perpendicular to the soil sample, perpendicular at all points perpendicular to the soil sample. So that is the confining stress, or the cell pressure as we say. So that is the cell pressure as we say, or that is the confining stress, or the confining, total confining pressure, all right. So total confining pressure, whatever it is there in situ, as we have seen here in this case, all right. So if we see here in this case, so we have one element here, so we have sigma 1, sigma 2 and sigma 3, all right. Basically here in the triaxial, what we will do is we will consider sigma 2 is equal to sigma 3, and in fact we can also control the pore water pressure. We will see that how we can control that. So we can apply sigma 2 and sigma 3, and then with the help of the loading ram we can apply the sigma 1. So we can also simulate the loading conditions, all right, in the soil as we have seen. So we can also simulate the loading conditions, so with the help of the loading ram, all right. So this is the basic setup, right? So we have a, extensive setup of the triaxial. So we have the loading, equipment here. We have the triaxial cell here. Inside the triaxial cell, we will have the sample, and of course, there are different sensors and various things where we measure the different um, parameters of the test. What are the different parameters? We will see. All right. So we have the loading ram here. So we measure the load. All right. So the axial load we measure. Axial load we measure for different confining stresses that we apply. All right, so we apply the water pressure, water pressure into the water, and through there the pressure is transmitted into the cell, inside the cell the pressure is transmitted. So that is the confining stress, that is the confining stress or confining pressure. All right, so that is the total confining pressure. Right, so that is what we are applying. Axial load we are applying, these all these two parameters we will apply. All right, and we will see the behavior of the soil. So first of all, we collect the soil sample inside a thin walled sampler, inside a thin wall sampling tube, and then we take it out, the sample we take it out. All right, we place it in the pedestal here. So the pedestal will have fixtures, all right, to control the drainage from and within the soil. All right, so if we want to control the pore water pressure within the soil, if we want to control the pore water pressure within the soil, we can do that. There are mechanisms within the triaxial test setup apparatus, so we can also control the pore water pressure, not only the confining stress or confining pressure and the axial load. So we encase the sample in a rubber membrane. Of course, this is already a failed sample. I could not come up with a picture where there is an, after putting it there, where I've encased it in the rubber membrane. All right. So this is already a failed sample. Anyway, so thing is that we put the sample here and we encase it in the rubber membrane. So the cell water in the cell, it cannot penetrate into the soil. Only thing is that it will put the pressure into the soil sample. So we have the various measurements. All right, we have the various measurements. So we have the uh, first of all, we have the cell pressure. So from here we apply the cell pressure. So as soon as the cell pressure is applied, so it will act on all points of the sample, top, bottom, everywhere. All right, so it will act at all points, and at all points normal to the sample. All right, in fact, as we know, cell pressure, water pressure, it will act in all directions. So on the walls of the triaxial cell also it will apply. So in the entire liquid that is filling the cell, that pressure whatever we are applying, so if we are applying 100 kPa here, suppose if we are applying 100 kPa here, this 100 kPa will be transmitted all throughout in the cell. So that is the confining stress, that is the confining stress. Now once that is applied, we can control the drainage of the water from the soil or into the soil, or we can measure the pore water pressure variation in the soil through the attachments which is leading directly into the soil sample. So we have the porous stone here, right, and the rubber membrane is encasing the entire soil, so there is no chance of water seeping into the soil from the cell. All right, only thing is that whatever pore water pressure, if we want, we can allow drainage into the soil sample and also from the soil sample, and if we want, we can measure the pore water pressure. Stopping the drainages, we can measure the pore water pressure. So that is the basic advantage of the triaxial cell. Then once this is done, we apply the axial load or the deviatoric load. We apply the deviatoric load. So this is sigma d, right? So sigma d plus sigma 3, we will have sigma 1, which is applied on the top cross-sectional area of the soil sample. So the same load will be transmitted through the bottom as well. So we have sigma 1. So if we draw the sample like this, we have sigma 1 at the top, sigma 3 from all sides, sigma 3 from all sides, all right, and sigma 1 as well on the bottom. So axially we have sigma 1 and from all sides, so sigma 2 is equal to sigma 3. So that is the axisymmetric condition of loading. So that is the triaxial test which we do. So this is sigma 3. We can allow the sample drainage. All right. So if you remember the Pascal law, if here we apply one cell pressure, so the cell pressure is equally transmitted in all direction. All right. So that is the basic concept that we use to apply the confining pressure onto the soil. All right, using the fluid in the triaxial cell. And then we apply the load, the deviator stress, right, and we measure the pore pressure or we measure the volume change, as the case may be. We will see later on. All right, and this is the cell pressure. So what are the things that we can do in the triaxial test? First of all, we can control the confining stress, control the total confining stress. So that is sigma 3. So in this apparatus, we can control the sigma 3 and we can apply that to the cell. All right. Then, so this is one. The second thing is we can apply the load, all right, into the soil sample to cause shear failure of the soil. All right, apply load to cause shear failure of the soil. So that will be the sigma deviator. All right. And what is sigma deviator? It is basically the additional amount of stress that we apply apart from the sigma 3 to cause the shearing of the sample. The sample will be sheared in this manner. So we have sigma 1. If we want to measure the sigma 1 is equal to sigma d plus sigma 3. So that is the sigma 1 in this case, if you want in terms of principal stresses. So this will be the major principal plane and this will be the minor principal plane. Then apart from that, so these are the two, so this is number 2. All right. So apart from that, we want to measure the pore water pressure within the soil, so we can do that as well. All right. So we can measure the pore water pressure. All right. Not only we can also measure the changes. Constantly we can keep on measuring. All right. So we can measure the changes as well within the pore water pressure. All right. So we can measure the changes in pore water pressure. All right. Now if we want to do a drained test, all right, we will see what is drained and undrained. So in that case, we can also control the drainage from and within the sample. All right. So if we want to control the drainage from and within the sample, so we will also have the drainage control. So in that case, what we will measure is the volume change of the sample. So we will measure the delta V of the sample, the volume change. Of the sample. So if water flows out of the sample, that means the volume of the sample is now reduced. So basically void ratio of the sample will, or the porosity of the sample will get reduced. If there is drainages into the sample, that means the volume of the sample is now increased. So basically the porosity or the void ratio of the sample will increase. So that is what we can measure. So we can, this is number 3, all right, and this is number 4. So we can see that various parameters of load which is applied on the soil, all right, shearing of the sample, all right, pore water pressure changes, all right, if we want to measure the changes in the volume. All right, all this we can control, and in a controlled environment we can do that in the laboratory. In a controlled laboratory environment we can obtain the behavior of the soil. We can measure, now we can measure the deflection of the soil in response to the applied load. All right, we can measure the volume change of the soil in response to the applied load when they will apply sigma 3, when we will apply sigma 1. So we can measure the volume change, we can measure the axial strain. All right, we can also measure when the soil will shear, what is the failure axial or principal stresses. All right, so we can draw the Mohr circle as well. So we get the sigma 3 here, we get the sigma 3 here, we get the sigma 1 here, and we can draw the Mohr circle as well. All right, so if we do two three tests, we can do the we will come to that in the next slides. So here we have the sample. So basically we have the sigma 1 here, we have sigma 2 equal to sigma 3, so sigma 3. So on all planes which are vertical of the sample, all right, so all planes which are vertical, so we have the sigma 3. So those are the basically the minor principal planes. All right, and all horizontal planes of the sample, so they will be basically the major principal plane. So this is the major principal plane, and these will be the minor principal plane. So we have the major principal plane and the minor principal plane, and then we will see where it fails. So we may have one failure surface as well, all right, of the sample. So in that case, if the sample fails, so in that case we have to determine what is the normal what is the normal stress, all right, total normal stress on the plane, total normal stress on the plane from in relation to sigma 1 and sigma 3. All right, and then we will also obtain the shear stress on the plane. All right, and we can also measure the pore water pressure if there is any pore water pressure development. So we can also measure the pore water pressure. So the pore water pressure will of course act normal out of the plane. So in that case the total effective stress, normal effective stress, will be sigma n dash equal to sigma n, which is the total normal stress minus the pore water pressure. So we see that the effective normal stress is reduced, but the shear stresses is remaining same. So since the shear stresses is remaining same and the effective stress is reduced due to the development of pore water pressure, so what happens? The confinement within the soil is now reduced and the soil may fail at a lower load of sigma 1. So we will see what happens in that case. So we need to do at least 3 tests at 3 different confinements. We go on increasing the confinement. Sigma 3a is less than sigma 3b is less than sigma 3c, and then we will have the loads here. So if this is p1 which is less than p2 which is less than p3, so divided by the area, all right, of cross section, divided by the area of cross section, we will have the sigma d1, sigma d2 and sigma d3, which is obviously in this range. So this plus this, we will have the sigma 1a, sigma 2a and similarly sigma 3a. So we will have sigma 1, this one sigma 3a, for this confining stress sigma 3a, we will have sigma 1a here. All right, similarly sigma 3b, we will have the failures load here. All right, and sigma 3c, we will have the failure here. So taking this sigma 1 values, all right, we will plot it here. So this is sigma 1a, sigma 1b and sigma 1c, and we will have 3 more circle corresponding to that. All right, we will have 3 more circle, and ultimately if we draw the tangent to the Mohr circle, we will have the c and phi, whatever the case may be, of the soil. So depending on the soil, this particular inclination, or there may be some intercept in the y-axis. we will see what are the different conditions. So ultimately thing is that we do 3 or 4 tests and we get the Moore circle and we plot the Moore Coulomb failure envelope. So basically what happens is that as we go on increasing the confinement, the soil compaction or the density of the soil goes on increasing. So basically the contact to contact, contact of the between the different particles, it goes on increasing, and the effective stresses goes on increasing. So we will have a higher, require a higher shear, strain or stress to cause the failure of the sample, So, so here we see some sheared sample. Here we see some sheared sample. All right, so there is some bulging as well. So when there will be bulging, when there will be shear, we will come to that in the later chapters. So to know the analysis of triaxial test, we need to know what is the total stress, what is the pore water pressure. So we have already understood what is the pore water pressure under hydrostatic condition. All right, so we know that the effective stress is sigma dash equal to sigma minus the pore water pressure, which is the difference of total stress to the pore water and the pore water pressure. And of course, the thing that we need to know is the excess pore water pressure development, that is delta U. So this is an important parameter which we need to understand how it develops, when it develops, all right, and how it will affect the behavior of the soil. So this is an important parameter. All right, in case of liquefaction also, what happens is that the excess pore water pressure develops. So ultimately what happens, it develops so much that the total, it almost becomes equal to the total stresses which is acting on the soil. So in that case, what happens, sigma equal to minus sigma u plus delta u is equal to, it becomes 0. So effective stress becomes equal to 0. So in that case, the soil, it behaves like a viscous liquid. So that is the case of liquefaction. So we will come to that in the later chapters. But just to show you that this is a very important parameter and we need to know how it develops and how it affects the behavior of the soil. So triaxial test, when we do the triaxial test in 2 stages basically. All right, so one is application of the cell pressure, and cell pressure means when we put the soil inside the cell. All right, so we increase the pressure in the water which in the triaxial cell. So that is the application of the cell pressure. All right, so what happens with increase in the cell pressure, the soil, if it is undrained case, of course it will remain unconsolidated. So in that case, the pore water pressure will develop. All right, so we will have increase in delta U. If it is a drained case, all right, if it is a drained case, so in that case, whatever stress we apply, so what will happen, it will squeeze in the sample. All right, it will squeeze in the sample and there will be some amount of drainage of pore water from the sample. So in that case, whatever increase in delta sigma 3 will occur, so that will result in delta sigma 3 dash of the sample, that is the effective confinement or the effective stresses within the soil will increase. So that is the application of the cell pressure. So that is stage 1. Then we apply in the stage 2, what we do is we apply the deviatoric load. All right, we apply the deviatoric load up to the point where the sample fails, where the sample shears off. All right, so the sample basically shears off. As we have seen in the previous slides, we have seen the sample will shear off. So up to the point the sample shears off, we apply the deviatoric stress or we apply the deviatoric load. Now in that case also we may consider 2 options. One is when the pore water pressure is not allowed to drain. All right, so in that case the pore water pressure, excess pore water pressure will develop, so delta U will develop. So delta U may be negative or it may be positive. When it will be negative, when it will be positive, we will see in the in the coming slides. All right, but thing is that it is undrained, so drainage will not be allowed, and therefore pore water pressure will change. In the other one, in the other application of deviatoric load stage, what we do is we drain the sample. So in that case, uh, there will be no development of pore water pressure, but there will be drainage into the sample or out of the sample. All right, so we will see when it is into the sample, when it is out of the sample. Obviously, if the sample it is such that there is development of negative pore water pressure, definitely that means in the drainage case, the drainage of water will take place into the sample. All right, and if the pore water pressure is positive, change in pore water pressure is positive, excess pore water pressure development is positive. So in that case, if it is drained case, all right, that sample, in that sample the drainage will take out of the sample. All right, so we will see what are the different cases. So basic thing is that one is undrained shearing and the other is drained shearing. So we have two stages. One is application of cell pressure, and the other is application of the deviatoric load. All right, and in both cases it may be drained, all right, it may be undrained or drained, all right, and again in this case also in the application of deviatoric stress it may be undrained and drained. So based on the drainage conditions whatever we have discussed here, we can now devise three types of triaxial test. All right, so we can now devise three types of triaxial tests. So what are the three types of triaxial tests that can be done? So one is the in the application of cell pressure, the sample is unconsolidated, all right, and in the case of application of deviatoric load also, it is undrained, all right. So the drainage conditions is not allowed at any stage of the triaxial test. So basically that is unconsolidated and undrained, all right. So that is the first and the simplest test, but of course the results needs to be thoroughly checked because it is also the most erroneous, all right, and it actually uh, we need to be very thorough with the analysis process, all right. Now the second one is when we allow the drainage of the sample, all right, we allow the drainage of the sample in the cell pressure application stage, all right. So we apply the cell pressure and we allow the drainage of the sample. So in that case the sample will get consolidated, all right. So that is the consolidated. So drainage is allowed in the consolidation stage or in the cell pressure application stage, all right. Then the drainage is stopped and the pore pressure is measured, right. The changes in the pore pressure is measured while shearing, while application of deviatoric stress is occurring on the sample. So while shearing we apply the deviatoric load and we stop the drainages, we measure the pore pressure changes. So that is the undrained case, right. Now of course in the third case, when drainage is allowed at all stages, we have the consolidated and the drained shearing, all right. So consolidated sample and drain shearing of the sample. So these are the three different types of tests which can be devised in the triaxial test, and in fact these three conditions are sufficient enough to replicate most of the in situ conditions which we will encounter, all right. So to replicate most of the in situ conditions which we will encounter in our practical geotechnical engineering, so these three conditions are sufficient, all right, as we will see in the the next classes. So what is the unconsolidated undrained triaxial test? So first of all we obtain the specimen, all right. So now when we take out the specimen from where it was, now the stresses in the sample, all right, the stresses in the sample, if you remember I was placing the sample on the pedestal, all right. So there was no stress on the sample, all right, no cell pressure, no pore water pressure. So pore water pressure was there, obviously we will see why how the thing is there, all right, but horizontal stress Vertical stress, it is nothing, only atmospheric pressure is there, which we actually consider as the axis. All right, so that is atmospheric pressure, we consider the axis, so we can consider that sigma v and sigma h on the sample is basically now 0. All right, so this is the stage when we place the sample on the pedestal, as we have seen in the previous slides. All right, then of course the pore water pressure, while taking the sample out of the this position where it was. All right, so the sample was here in this place, so we drilled the hole, and we used an undisturbed sampling, and we took out the sample. Now from the sampler, then we took out the sample and we placed on the pedestal. All right, we placed on the pedestal. Now here what happened, here there was a pore water pressure acting on the sample, and there was total stresses acting on the sample. Now suddenly all of these are released. All right, all of these are released. So what will happen is that the pore water pressure will now be the negative value of what it was here. All right, so that will be the, now that means in the pedestal, when it is on the pedestal. All right, so that is the case. So we obtain the specimen and we place that on the triaxial apparatus. All right, we have not yet put the cap on, and we have not yet put the water pressure as of yet. So we have these conditions here. All right, so effective stress, all right, effective stress, what we will have is, we will have a negative effective stress. So that is why the sample holds. All right, so we will have a negative effective stress. Negative pore water pressure, whatever is the effective stress we will have in the sample. Now what we do is in the next stage, we first of all we encase the sample. We encase the sample here, all right, with the rubber membrane. With the rubber membrane, we encase the sample, and then we put the cell pressure. We put the cell pressure on. All right, so we put the cell pressure on. So as soon as we put the cell pressure, that is sigma C, now we put the sigma C. So sigma V and sigma H on this sample will be the confining cell pressure, right? Whatever we are applying. Now here there will be change in pore water pressure. That will be depend on the parameter B. We will see what is the parameter B, right, in the next slides. So thing is that as soon as we apply confining stresses, what will happen is that there will be a the sample will be squeezed on again. All right, so as soon as it will be squeezed on, so the pore water pressure will now again from the negative state, it will now come to the positive state. All right, so initially what happened, it was released here, everything was released, so the pore water pressure was the residual pore water pressure what was in the sample there. All right, as soon as it was taken out, so we had a sigma 1 acting, all right, sigma 2 acting, sigma 3 acting. Now it became 0, everything is 0, but the pore water pressure, it is still there, all right, in the sample. So now when we apply the cell confining cell pressure, the sample is now again squeezed on. All right, so now we will have a effective stress which is equal to the confining pressure which is applied, all right, and the pore pressure which is within the soil sample. All right, so we will have effective stress sigma dash equal to the confining cell pressure applied on the sample minus the pore pressure within the sample. All right, minus the pore pressure within the sample. So this is the effective stress. It is now in the soil sample, which is existing within the soil sample. Then in the third phase, what we do is, so we have obtained the sample. All right, we have taken out the sample from the sampler, we have placed the sample in the cell. All right, and then we have increased the cell pressure. All right, we have increased the cell pressure. All right, we have applied the cell pressure, and then now what we do is we apply the load. We apply the load. We keep on applying the load until there is a failure in the sample. All right, so that is the third phase. So first is consolidation phase. All right, or cell pressure application phase. Cell pressure application. So that is a stage 1. So that is stage 1. Stage 2 is deviator load application or deviator stress application. All right. Now, what are the stress condition, how it develops, all those things we will discuss in the in coming classes. But thing is that here, how we do the triaxial test, that is what we are discussing. So this is, of course, the unconsolidated undrained one. All right. So in this case, here we have not allowed drainage to occur while application of cell pressure, and while application of deviator load also or deviator stress also, we have not allowed drainage from the or into the soil. All right, but we can measure the pore pressure if we want. All right, we can measure the pore pressure. So we will see the analysis of the result in a later classes. So thing is that no drainages allowed in any stage. So this is unconsolidated undrained. All right, why it is unconsolidated undrained, we will see. Now in the consolidated undrained triaxial test, again as in the first case, we obtain the sample. All right, we obtain the sample, so there is some residual pore water pressure. All right, so that we have the effective stress. All right, so we have the effective stress here. All right, so we put the sample in the triaxial cell, and in the second stage, that is when we apply the cell pressure. When we apply the cell pressure into the cell, all right, we apply the confining pressure onto the sample. So while applying the cell pressure onto the cell, what we apply is that we allow the drainage from or into the sample, whatever the case may be, to occur. All right. So basically, the pore water pressure now is 0, as the case may be. All right. So basically, the delta U excess pore water pressure is equal to 0. We will see what is the difference. So excess pore water pressure development is not occurring, and we are allowing the pore water pressure to dissipate through drainage of pore water from or into the soil. So this is the stage 2. So in the consolidation stage, so this soil is now getting consolidated. All right. So whatever confining stress or confining cell pressure we are applying, the same amount of effective stress is being developed within the sample. So that is what is happening here. All right, so the effective stress is equal to whatever confining cell pressure we are applying. So this is what is the case here in the consolidated triaxial test. All right, so and then what we do while applying the deviator load, now this is consolidated. Now while applying the deviator load, what we do is in case of applying the deviator load, we close the drainage. And we keep on monitoring the pore water pressure development within the soil. So the volume change is now, there is no volume change in the soil, and as we apply the deviator stress, as the deviator delta sigma 1 is going on increasing, so there will be changes in the pore water pressure when there will be shearing. So we measure that pore water pressure. All right, so ultimately there will be a change in the effective stresses in the soil as there is changes in the pore water pressure. So in this case, while shearing is occurring, while the loading is applied onto the soil, axial load is applied onto the soil, there is change in pore water pressure and therefore change in the effective stress. All right, and then we determine what is the failure, when the soil sample shears, what is the load which is being applied, what is the cell pressure, and what is the pore water pressure. All right. So ultimately, based on that, we do the analysis. So all of these properties, all of these parameters, we keep on measuring and monitoring. All right. So that is the consolidated undrained triaxial test. Now, in the consolidated drained triaxial test, as before, we again start with obtaining the sample. All right, so there will be some residual pore water pressure. So this is the effective stress state. So we put the sample in the triaxial cell and we apply the cell pressure. So while applying cell pressure also, we apply for we allow the volume change. So the pore water pressure or the excess pore water pressure is equal to 0. So whatever confining stress, all right, or confining cell pressure we are applying, the same amount of effective stress is being developed. So effective stress is equal to confining the confining cell pressure which is applied. So this is the consolidation stage. All right, so the sample is basically consolidated to the confining load that we are confining stress that we are applying. All right, or the cell pressure that we are applying. Then, so this is stage 2. Then in stage 3, when we apply the deviator stress, so in this stage also, what we do is we allow the volume change. So in this case also, there is no change in the pore water pressure. So, but there is volume changes in the sample. So the sample may expand or it may compress depending on the property of the soil. Of course, we will see when it expands and compresses. We will see in the later classes. So in this case, while we apply the deviator load, the thing is that we allow the volume change to occur. That is drainage from or to or from the sample to occur. So excess pore water pressure generation is not there. So whatever axial load is applied, we have the effective vertical stress, all right, or sigma 1 dash is equal to, first of all, the confining cell pressure, all right, plus the delta sigma A, all right. So delta sigma A means the axial load, all right. So the axial load. So this is delta sigma 1, and of course delta sigma 3 will be equal to the confining cell pressure which we are applying in the soil, all right, or through the cell pressure. Right? So this is the 3 different triaxial tests. Of course, in the later classes, we will try to understand what is the physical relevance of the drained and undrained condition, and what is the relationship of the stages of consolidation to the effective stress distribution within the soil. All right, so this is a very important understanding, and we need to visualize what is happening within the soil samples so that we can understand and we can do the analysis properly from the triaxial test data. All right, so these are the 3 different triaxial tests that we do. All right, and what is a triaxial test basically. All right, and then we will come in the later classes how to do the analysis, how to go about the analysis of the triaxial test data. So basically the thing is that in the triaxial test we can control the total stress, we can control the total stress, all right, and we can apply the deviator load. All right, we can apply the deviator load. So we can apply the deviator load, right, and the most important part is that we can measure or we can monitor the changes in the pore pressure. All right, we can monitor the changes in the pore pressure or pore water pressure. So this is very important 3 points of the triaxial test. All right, so we will first of all today we will stop here because it is already time. So we will continue in the next class.